The moment you've all waited for, time to shut up. Tonight, we have designing and assembling temperature satellites. Everything you ever wanted to know about a CubeSat, putting it up in space. We have Abigail, KN6 SOT, and Cole, KN0 TCF from CalPoly CubeSat Laboratory. And they're going to talk to us about what to do with the satellites.
Hello, can you hear us?
Yes.
Great. Hi. Great to see you all. My name is Abigail, KN6 SOT. This is Cole.
Hello, how are you guys all doing?
So we have sort of a two-part presentation for you tonight. The first part is going to be Cole talking you through basically just what we do as a lab, the hardware that we generate, what we do, I guess, on a daily basis, and some of the stuff that we've done in the past. And then I have a presentation for you on the communication side of things, and the radio antenna applications, what we do in lab, what our ground station looks like. So yeah, we'll get right into it with Cole's lab and hardware tour here, and we plan to take questions at the end.
Alrighty, hello everyone. So this is a CubeSat. You can see this one's nice and encased up in a display case. This is one of our old missions, IPEX, that flew back in 2013. And this, you can see about 10 centimeters by 10 centimeters. That's the CubeSat specification. And so that's what we do here is we design, build, and fly CubeSats just like this one. And so are you guys still able to hear me when I'm over here?
Yes.
Great. So this right here is a 3U CubeSat. This is ExoCube 2. It's one that is our most recent successful flight mission. It actually went up, I think, in 2019. And so this was, again, built and designed by students. And so this here is a 3U CubeSat. The one that we were looking at before is a 1U CubeSat. And all CubeSats come in some way from between, that 1U that we were looking at earlier and this 3U here, all the way up to even a 6U, which is kind of two of these right next to each other. The reason for that is because the way that we actually get these to space is they fly on a deployer that looks a little bit something like this one right here. And so a CubeSat deployer is basically like a large Pez dispenser. And so the way you can see, it's got a door out here on the front, and then it bolts on to the main part of the rocket on the back. And in here, you can fit 3U worth of CubeSat. So either 3 individual 1Us or a 3U like I was just showing you. And so that's kind of what the CubeSat spec is based on, is we can put any type of CubeSat that fits the spec into a deployer like this, and we can use any deployer that fits the spec to fly our CubeSats. And so that's really allowed for the market to explode in this small satellite space and allow for lots of different people to develop all kinds of different missions using these specifications. So CalPoly was the ones who, working with a professor at Stanford, there was a professor here at CalPoly who came up with this specification and really led the charge on developing CubeSats. And so I've got a poster here of some of the first CubeSats that we created back all the way, CP1, CP2, CP3. These are some of the very first CubeSats that ever launched. They were launched on basically recommissioned Russian nuclear weapons that had been turned into launch vehicles, and that was what we flew on. And these were really just test missions to test out all kinds of different sensors, hardware, our initial communication systems. You can see some of the antennas that they have on there. We'll talk about it later. And that was really how the lab started. Since then, we're now ExoCube 2 is CP13. We've successfully launched, I believe, 9 missions, and a number of these, including a bunch of these, were unsuccessful. A lot of the first initial tries didn't actually come through as we wanted them to. Today in lab, a lot of our focus has moved away from maintaining the CubeSat specification, and instead what we end up doing is we focus on developing new technologies that we can apply to the CubeSat world. And so one of those examples is when we were looking here in ExoCube 2, it's got reaction wheels in there. So in here, there's a wheel that spins around, and allows us to really precisely control where the satellite's pointing. And that was important for the science payload that was on this mission. Currently, some of the experimental missions that we're working on are what we like to call pocket rocket. You can see here the fire test, and the idea is it's building a 1U, so the size a third of one of the satellites, that has a thruster on it, an ionic thruster that we ionize. We're looking into a number of different gases and are able to then turn that gas into propulsive thrust, and now we can use that to control our satellite and change our orbit. Some of the other work that we're doing has to do with systems engineering and a lot of the fundamentals in terms of how do we develop a satellite, break it down into subsystems, how do we then set up requirements and do a risk matrix to be able to understand what are the different risks that a satellite like these CubeSats might undergo as we're developing them and then as well flying them. So the last couple things I wanted to talk about. I also want to show you guys, here's a 2U satellite. So you might have one of these with another 1U on it inside of that deployer. And among all these different missions that we've flown, we've managed to get up a number of different exciting science payloads. Our most recent one that's been talking to us for almost 5 years and just recently was decommissioned was DAVE, which is the dampening and vibrations experiment. And that satellite was testing out dampening of vibrations, funny enough. And so from that, we were able to get some really interesting data about how we could dampen vibrations in a 0G environment. And doing it not in the scale of a room-sized satellite that you would have to pay millions and millions of dollars to produce, but in a single 1U CubeSat. And that's a much cheaper way to get stuff up to orbit. And that's kind of what CubeSat's about, what we're about. So now I'm going to pass it over to Abby to talk some more about our comm system specifically.
Hello, I am going to share a PowerPoint with you. Here we go. All right, we trial ran this earlier, but let me know if you guys cannot see the screen. So yeah, like Cole said, this is just going to be us going a little bit further in depth about our comm system and how we use, our UHF setup and our antennas to communicate with the satellite, because we felt that that was perhaps applicable to this group. So getting right into it, from a top level overview perspective, there are two on-orbit deliverables that are generated by the CubeSat while it's in space. The first is a telemetry beacon. And those are transmitted every couple of seconds automatically, regardless of the power mode, operational mode, and regardless of whether or not it's actually over our ground station at CalPoly. So for that reason, these are often received by amateur operators and other operators who are all across the world, which is really cool. These packets are lower precision data, and they're only a few bytes. And we modulate them in Morse code, so they can be easily demodulated and read by essentially anyone who receives them. Also, on board the satellite, every 5 minutes, the sensors are pulled by the main flight computer, and all of the responses to the sensor pulls are stored on board in the SQLite database aboard the satellite. Every 3 hours, the satellite generates a telemetry export file, and we put in an uplink request for that file specifically, and then it's downlinked on request. It's just higher fidelity data, larger in size, more precise. So if we receive a beacon or a smaller packet that tells us that there's some off nominal readings with our onboard sensors, then that's the point where we would download the large file for troubleshooting, or if we wanted to downlink just a large telemetry packet, if that was a scientific payload. So this is a diagram representation of what I just talked about. Basically, the satellite in orbit collects data, and then it downlinks a beacon every few seconds automatically, and then on request, you can download the telemetry export file. The beacon goes directly to our mission server, and it's decoded by our database logger, and then it's stored in the telemetry database. The telemetry export files go through our auto or manual operator, and then are also stored in the telemetry database, and then those can be accessed via our client-side applications by ourselves or our clients. As far as our modulation schemes go, we use Morse code for the beacons, and then we use AX25, which is FSK for most of our payload data and telemetry. We use a standard operating frequency of 437 plus or minus 5 megahertz, which I don't need to tell you this, but it's in the middle of a giant amateur band, which is useful. So one of the nice things about the CubeSat specification is that everything is a standard size, and oftentimes the satellite bus is standard from mission to mission, even if the payloads on board are different. So we have had a couple of iterations of our flight hardware, but for the most part, the flight hardware remains consistent from mission to mission. So our existing architecture is we have a UHF daughter board, which is attached to the main flight computer, which we call system board. I believe we're on system board 3. It's hard to see here because it is shielded, but the UHF daughter board is the attachment on top that has a little piece of Kapton tape on it. And then we have what we call the -Z board, which is our antenna and RF board. And I will talk a little bit more about those going forward. This is the layout for our UHF board. I won't go into great detail on this slide because it's a little self-explanatory, but essentially the UHF board interfaces with the system board, which is the flight computer, via SPI. And then on the other end, it interfaces with the Z board antenna, presumably also by SPI, although we didn't label that. So our flight antenna utilizes an L dipole, which is deployed on orbit using a burn wire. Essentially, you just put a lot of current through resistors that get very hot, and then it melts a wire. I have a video right here of it deploying. Hopefully this plays.
Oh, it's burning. There we go.
So yeah, basically you just have a very tightly tensioned wire, and then when you burn that, the antennas just spring out into the L dipole formation. And because not all of our satellites have active control, sometimes they're just tumbling through space without any sort of internal ADCS mechanism that's governing the orientation in space, and it can just be tumbling out of control. So for that reason, it's beneficial to have an antenna that is going to be omnidirectional as far as the flight hardware goes. So here at CalPoly, we have 3 ground stations. The first is Hertz, and it utilizes 2 directional Yagis, one for 70 centimeters and one for 2 meters. That is from M2 antennas. And then also on the same roof right next to Hertz, we have Marconi. Those are down here at the bottom. Marconi is 2 directional Yagi antennas that are phased as one for 70 centimeters. And then we also, photo not included, make use of an omnidirectional discone antenna for 2 meters. That model is, and I'm not sure if this has any significance outside of lab, but that's an M2 436 CP4 2UG. Which is the same model that we use for Freeze, which is our quad Yagi, which is 4 directional Yagis phased for 70 centimeters. And that one was constructed in 2015. So the actual hardware on it is a little more up to date. Hertz and Marconi have been around since, I believe, CP1 and 2, which were in the early 2000s. So we do continual upgrades on them, but for the most part, they are as they were constructed. So Freeze was our most recent development with the goal of producing a higher gain directional antenna that could be used for missions with higher data rate requirements, as well as missions that are substantially farther away. Like for instance, if we were to launch a lunar CubeSat. Cool. So we require a technician class or higher license to operate the ground station because our satellites are in amateur bands. So for that reason, even though we aren't an amateur radio club, we have one on campus. We still have most of the members of our lab are licensed ham operators, which is cool. Oh, I've been informed I'm talking too fast. So there are 2 operational modes for our ground station. The first is automated operations, and that is configured before launch through our network called SatNet, which I will go into detail on later in this presentation. But we also have the option to do manual operations, which is when the operator interacts with the ground station components manually. So the idea with that is that even if a satellite has already been launched or it's already on orbit, you have the option of loading that 2-line element into our tracking software and then communicating with the satellite, even if it hasn't been configured prior to launch. So this is maybe a lot of information for this slide, but this is just an example of the block diagram for Marconi, which is our dual Yagi setup. And I'm going to go more into detail about the hardware on that going forward. So not critical that we get all this down at once. So recently we've upgraded all of the stations to software-defined radio. So we make use of an RTL SDR for Hertz, and a Hack RF1 for Marconi, and a FunCube Dongle Pro Plus for Freeze. But we also still have the legacy hardware radios in the setup. We make use of Cantronics terminal node controllers for Hertz and Marconi, and we have upgraded to a software terminal node controller for Freeze, which is our more recent one, the Quad Yagi. For the rotors and controllers, Hertz and Marconi, which are the duals, use a Yaesu G5500 and the corresponding controller. And on the Quad Yagi Freeze, we use a SPID Big Ras HR rotor and a Green Heron RT21 controller. And that RT21 controller is very handy because it makes it very easy to do manual operations using the point and shoot elevation and azimuth controls on the box itself. So we have 3 software programs that we have implemented to operate the rotors for satellite tracking. One of them is for a Mac interface, one is for PC, and one is for Linux. In my opinion, the most intuitive is Mac, which uses Mac Doppler, which accepts a 2-line element, which I will go into a little more detail about in the next slide, to predict the satellite location as a function of time. So essentially you just can propagate the orbit of the satellite, and then you can tell your antenna where the satellite's going to be. And then the program that we have written accounts for Doppler shift as well as the actual rotor control. So you basically just have to feed it the 2-line element for your satellite and it can track it automatically. The PC and Linux interfaces are similar to the Mac Doppler, they're just slightly different. So down here I have example of 2-line elements for CP3 and 4, as well as the ISS. And then this is just a photo of what that interface looks like. So as far as 2-line elements go, it is a data set that's generated by like NORAD and the US Space Command that allows you to propagate the orbit of any cataloged object in Earth orbit. So let's see, how do I explain this? Basically, what?
You want me to talk about it?
Yeah, you can.
Sure.
Cole's gonna explain this a little better than I can, I think.
Yeah, so these 2-line elements are a really simple and unified way to understand where a spacecraft is at a certain time. And so these get updated. For some things, it's every day or every couple of hours. For some other objects like the ISS, these are updated, by the minute. And so these give a really accurate, it gives all the parameters that you need to really accurately model an orbit for any given object in space. It doesn't even have to be a satellite. They do these also for space junk. And you can see the way that it's laid out here. It's all just real simple encoding, real simple numbers. It's all defined in terms of, where you're supposed to have the decimal places and everything like that to keep it as simple as possible. And so this is, as we were talking about earlier in the beacon, this is what's sent down in the beacon. It's just this 2-line element that tells us really simply, this is where the satellite is. And so then from there, we can figure out, now that we know where the satellite is, and it also tells us how it's moving just based off of simple physics, orbital dynamics, we're able to then propagate that orbit forward. We can understand where is it going to pass overhead of our ground stations so that we can point them in the right direction as it's coming overhead.
Thank you, Cole. All right, moving along. So on the software side of our ground station setup, our network is referred to as SATCOM, and that is comprised of the SatNet controller, which is our ground station control, Sat Live, which allows us to view information about currently tracked satellites, and OpenMCT, which is our telemetry visualization software. So the first of these is SatNet, which is a UI that we created here in lab. It essentially is the way that we set up the automated operations for AutoTrack. And we have an override mode where, like I said, you can do the manual operations using the point and shoot elevation azimuth controls, as well as you can load in the 2-line element after the fact to track the object. So essentially, this is just how we interface with the rotor on all of our antennas for tracking. Sat Live is a visualization tool that allows us to see where our satellites are. It gives us the ground tracks. This is a photo of ground tracks of a couple of our satellites that are currently on orbit. And we can load any satellite, even if it's not ours, into Sat Live just for visualization. You can see here on the map, our ground station is labeled here at CalPoly. And then you can also see the Purdue ground station. We do a lot of work with Purdue. collaboration on flight missions and things. And so for that reason, we also have the ability to log into their ground station setup for operations there. I'm not sure what the third one is.
It's another one that's in collaboration with Purdue.
Got it.
It's been offline for a little while now, unfortunately.
Cool.
Yeah.
Makes sense. Yeah. So SATLab is basically how you can see the ground tracks of your current and future passes. And it'll tell you, like, if you say, I would like to send if I would like to uplink a request for a telemetry export file from, you know, Dave, which was the one that Cole was talking about earlier, then it will tell you your next opportunity to communicate with Dave is going to be in 6 hours and the pass is going to be 12 minutes long. So it's a helpful tool for visualization and for, you know, logistically figuring out when you're going to be able to obtain data from your spacecraft.
Actually, go back real quick.
Okay.
And another thing to talk about on this is the way that we actually operate our satellites is really shortly after they launch, and we actually get the satellite up in orbit. It's been separated out from the launch vehicle. Now we have to run operations, and especially in that first week is really critical. At that point, we really don't do any automatic operations. Everything is done by hand here on campus. And so, you know, with these orbits being as they are, we might only get passes every 27 hours. And when you do the math on that, that means you'll be in here at 1 a.m. one day, you'll be in here, you know, 5 a.m. the next day, and then all through the afternoon. And so when that happens, it's a really critical time with those satellites, because when something is going to fail, it's going to happen in that first week. If it lasts that first week, it'll probably last its full lifetime. And so that's why having tools like this to make our entire workflow a lot simpler is really, really nice, so that we can plan those out accordingly and we never end up missing a pass early on.
Cool. All right. The third part of our software configuration is called OpenMCT. And this is a way that we're able to actually visualize our telemetry. The example used here is, once again, from Dave. It's the -Z board, which was the antenna RF board thermometer readings over time. It just allows for really easy, useful data visualization. So the database that we have down here at CalPoly reads directly into MCT, and OpenMCT is a software originally developed by NASA, which was integrated into our SATCOM network following Marco, which was Mars Cube 1, which was the first CubeSat that went to Mars by Dr. Ballardo, who is our faculty advisor. So that's a cool piece of technology that we have access to. It's a NASA standard, but it is really useful for us as far as telemetry visualization and like being able to very easily characterize the health and behavior of our CubeSats on orbit. So this is what our old ground station setup looked like. It has since been upgraded, but back in 1999, when we were first trying to, you know, set up what is our SATCOM network going to look like, how are we going to do operations for CP1 and CP2, they were all running off of these computers, and the computers are different, but a lot of the hardware is still the same that it was back then, and it still works very well. So that says a lot. So this is just our conclusion question slide. These are some photos that were taken, I believe, in 2013 by one of our missions. And Cole, do you have any more to say?
No, I think at this point we're open to questions. And so anyone who has them, you might have to get close to the mic to actually for us to hear you, but yeah.
Turn me up. All right, thank you. I have a quick question for you.
Yes.
How do you handle radiation exposure to some of the microprocessors?
Yeah, absolutely. It is definitely a big problem. Luckily, most of our satellites end up being in low Earth orbit. And so in low Earth orbit, you're below a lot of the big radiation bands that are out if you're trying to go further. But one of our recent missions that we've been developing, it's our collaboration mission with Purdue, was originally planning to go to GTO. So that's a geostationary transfer orbit, which means it's going all the way down close by Earth and then going all the way up to geostationary orbit, where, you know, all of your GPS or all of your big communication satellites and stuff are, everything that stays over a certain point on the Earth. And so that mission, since it was going to be going through GTO, it means it's going through the Van Allen belts, which are a big radiation region around the Earth. When we were designing that board, or when we were designing that system, we basically had plating inside of each of our electronics boards. And so I also brought over Dave here so you guys can take a look. This is Dave. here's that minus Z board that we were talking about. Basically, inside of each of these boards, there would be a layer that helps protect it from radiation. And that's really all that we would need for our critical components. A lot of the solution to that is actually done in software in terms of having lots of redundancy and lots of system checks to make sure that everything is running properly. Most of our satellites that we've flown in recent times have a process that checks out all every 5 minutes as it's doing that data collection to make sure that everything is running properly. And if it finds anything wrong, it gets put into a safe mode where the satellite can't do anything that will harm it, and it waits until one of the operators can get back in touch with it and figure out what went wrong. And so you're absolutely right. Luckily, with what we're working with, a lot of our components are already a little bit radiation hardened and aren't terribly sensitive to it, at least in the ways that would be mission critical or mission ending.
All right, thank you. Any questions?
Yeah. And I pulled up this photo here of the radiation shielding that we put on the UHF board, which is tolerant to all of the nominal radiation exposure that you would expect in low Earth orbit.
Thank you. Andy. I don't know, see if she can hear you. Can you hear him?
Just speak up, Andy.
Hear me okay?
We can't hear you.
All right. I had a question. What is the lifespan of these satellites? And then once they've lived a good life, what do you do with them?
You can do this.
Yeah. So most of our satellites end up staying up in orbit for about 3 to 5 years. Based on FCC guidelines, we have to be down by 25 years, but we mostly, as I was talking about, we're in low Earth orbit. And so what ends up happening is that normally the mission itself will only take maybe a couple of weeks, maybe a couple of months to collect all the data that we need. And at that point, the satellite just hangs out up there, continues, going around in its orbit as it was, until eventually, there's a little bit of atmosphere up there. Eventually the drag will cause it to come back down into Earth and everything will burn up in the atmosphere. And so nothing ever makes it back down to us. We don't get to recover them, however cool that would be. But in that time where, we have 4 years or something to where we have the satellite up there, we have cameras on a lot of our satellites. And so the pictures that you saw on the end, those last few slides, or even if you go back to the beginning, that one's a really good one.
Oh, I went too far. Here we go.
Students, a lot of times that's how we train people on how to actually operate the satellites, is going up there and requesting it to take a picture. There's a picture of Svalbard, Iceland, that one of our students took a bunch of pictures of, and to see the ice receding over the course of spring. And so cool little projects like that introduce people to the satellite communication, that entire setup that we were talking about, and trains them to be able to do the actual operations when we're doing mission critical operations.
Any more questions?
Yes. He asked already. I was curious also how long these satellites last, but also where are they typically launched from?
Good question. So we have done recently more launches out of Vandenberg Space Force Base, which is 40-50 miles south of here. The cadence of launches at Vandenberg has really increased recently because SpaceX is launching Starlink satellites like once a week out of Vandenberg at this point, essentially. So primarily we launch out of Vandenberg. Have we launched out of the Cape?
Yeah, we've launched out of the Cape. A lot of those original missions, CP1, CP2, CP3, all launched out of, I think it was in Ukraine was where that launch took place. And so, especially early on, it was all about wherever we could get a ride. And so we're never going to be the primary payload, these tiny satellites. The whole point is that they're going to ride along with whatever the big payload is. And so in recent times, there's been a lot of programs that NASA has developed, such as CSLI, the CubeSat Launch Initiative, that basically connects up CubeSat labs like us with those launch providers. And they basically pay for the ride up to space. And so those kind of collaborations are happening more and more all over the CubeSat industry. I think there's been CubeSat launches on almost every rocket that's launched in the last 4 years. And so it's really been, it's kind of a no-brainer to fill in that extra space, fill in that extra mass with really dense, technical payloads, exactly what CubeSats are.
It's also worth noting that CP1 and 2 out of Ukraine never made it off the pad. The launch vehicle exploded. So that's what you get when using repurposed warheads or miss.
Yeah.
Yeah. Yes.
All right, we got, so what is the average cost for a 1U to 3U CubeSat for creation? And what is, if you don't have backers for the launch, what is the average cost of the launch?
Yeah, so the launch for, the general rule of thumb is a 1U takes 30,000 to launch, and it increases by another 30,000 from there. The actual development of the satellite depends a whole lot on what the actual science payload is. So for example, ExoCube 2, the one that I brought up, the 3U, that scientific payload was almost a $2 million payload. And so building out that satellite, there was a lot more risk analysis that went into it, a lot more details that had to be figured out. For AID, which was the Purdue collaboration that I was talking about, that one was more on the order of $60,000, $80,000 overall total development cost. And so that includes a lot of the kind of infrastructure that we need to support the satellite, as well as the actual development of the satellite itself, doing revisions on the different boards, creating the actual mechanical structure, and then time for the staff members who are on staff here.
All right, thank you.
Yeah.
So,
If you noticed anything about the degradation modes, in other words, at a long Earth on orbit, obviously the performance has got to fall off a little bit, and do you have any speculation as to what causes that?
Yeah, I mean, it really depends on what you mean by performance. I think one of the really easy ones that I could point to is this picture that's right here up on the screen now. What's hidden behind the CVARC presentation that's there is one big black spot. There was something at some point that got onto the camera of Dave about 2.5 years into the mission. And since then, every single picture that we took with it has this one big black spot on it. And so we see degradation in a number of different ways. Most of the time, we don't see the kind of things that the ISS sees, because that's been up there for decades now. Since our satellites are only up there for a limited amount of time, and their mission critical phase is even shorter than that, most of those factors we don't really worry about. Since they're not part of the mission critical design, what happens afterwards is really just a bonus. And so we do what we can to make sure that we can succeed at the stated mission, and then beyond that we try and simulate, we see what might happen. Yeah.
thank you. Anyone else? Derek?
Yeah, I have a follow-up question to the radiation protection. Do you tend to use something with just high Z to shield it, or do you use red hard parts?
We lost you there. I couldn't really hear you.
Okay, when you shield your components, do you use red hard parts, or do you use high Z materials around it to shield it from radiation?
Combination of both.
Combination of both.
Yeah.
Okay, the other question too that we follow up is that I'm really concerned about SpaceX, whenever any Starlink components being space junk, and how do you plan to avoid that? It deorbits after 5 years, it's still garbage. It's going to hit somebody. How do you avoid that?
Yep. So that's actually, the mission that I've been talking about, the one that's a collaboration with Purdue, AID stands for Aerodynamic Deorbit Experiment. And so the plan with that mission is we're developing a half-U drag sail module that could be attached to any CubeSat to take that time down from 3 to 5 years down to basically 3 to 8 weeks. And so that's actually one of our missions that we're actively working on right now. We're in development. We're in the preliminary design phase right now, working with Purdue. And the goal is that this will be a commercially available module that will eventually be sold to all CubeSat developers. We foresee as a lab that those FCC guidelines are going to continue to get stricter because of exactly what you're talking about. Space junk is a huge problem in the space industry right now, and we're edging closer and closer to the time where we can no longer launch stuff to space because we've had some mass destruction event where it's destroyed all the satellites, and that could lock us out of space for 100 years or something like that. And so, yeah, it's something that's big on our mind, something that we talk about both in all of our classes here at CalPoly and within the CubeSat space, is making them as, since those missions are so short, we can bring them right back down afterwards is the goal.
Also, most of our satellites are made of, aluminum and substrate and 3D printed plastic pieces, and they will burn up in atmosphere. And it's very unlikely that one of them would make it through the atmosphere and hit someone.
Norm,
Have you ever discovered anything truly amazing or previously unknown?
Mhm.
I think probably the most interesting thing I could talk to is light sail. And so this was a solar sailing mission. And so it was the first ever solar sailing mission. Yeah, you can see the poster up there, kind of right up there behind me, if you look closely. But the idea with that mission was we were testing out this new technology. It was a collaboration with Bill Nye's Science Foundation to very similar, opposite of a drag sail though, deploy this big giant sail that would catch the photons coming out of the sun and use the tiny amounts of force that provides to increase your orbit. And so that one launched, I want to say in 2014, and was great success. It managed to raise its orbit just based on solar sailing alone. And that was the first time that technology has ever been tested on a satellite. It's something that we could potentially use for navigating around our nearer solar system in the future, with larger missions, maybe even human missions.
all right, thank you. Yes,
I can't get down there.
what's your question?
Yeah.
No, just about.
Yeah, Bill, K6HP. Question I have for you is, just want to clarify, what's the cost for launch? How much does it cost to, did you have to?
Oh, the cost per launch?
Yeah, and where does the funding, where does the funding come from?
Yeah, so variety of sources. Most of it is that whenever we're launching these payloads, since primarily what we do is we're a bus developer, like Abby was talking about, we end up using a lot of the same boards, our same communication system that's been flight tested. And that's really what people who want to fly payloads want to hear. They want to see something that's been used before. And so most of the time when we're working on a mission, whoever it is that has the payload that they want to fly. So for example, ExoCube 2 was an experiment that that NASA wanted to fly. And so NASA was the one who funded the entire mission. Same thing with this Purdue collaboration. There's a professor at Purdue that got a bunch of funding. I'm not quite sure where all that funding comes from, but they're the ones who got all that funding to run this experiment, to develop this new module. And so the money comes through them. So that's, for us, a lot of times we're the middleman. We're the one who takes whatever this new technology is, whatever the science is that needs to happen in space, and we build the satellite around it. We operate that satellite, and we make sure that all of that goes smoothly.
One other comment. I have faith in the future with you two. Very impressed by my older boy, Jeffrey K6HP graduated from CalPoly years ago. And you're very impressive. Thanks so much for your great presentation and your work.
Oh, great. Thank you.
All right, we have time for one more question, one more. James, how much does a CubeSat weigh? How much does a CubeSat weigh?
No more than 2 kilograms. Part of the CubeSat spec is the mass. And so for a 1U CubeSat, it weighs no more than 2 kilograms, which is what, 1.6 pounds? Yeah, 1.6 pounds at max. Sometimes that gets changed based off of the deployer that we're flying with, but most of the time that's about what we're looking at.
All right, great. Yeah, question, yes.
Yeah, Charlie K6CX, I'm curious how much of the power this CubeSat transmitter radiates.
Another question. Did you catch that question?
One more time, please. Or the
How
antenna.
Transmitting power.
That is not a number we're allowed to disclose.
What's the power draw? What's the daily power requirement of a CubeSat?
Very much dependent on what the payload is.
Yeah, anywhere from about is it watts? No.
Yeah, it's nominally
scale of
5 watts.
Yeah, from anywhere from like 5 watts to 40 watts, depending
40
on
that would be a lot, but
Yeah,
yeah,
depending
it
on the
probably gets
mission.
up that high.
All right, thank you. You had one other question?
Oh, yeah, it looked like we had for your receiver setup, we had 3 different SDR, commonly available SDR type receivers there. And also you said you're transmitting to 430 some odd megahertz with FSK frequency 15 modulation. And so you use just the readily available, if we wanted to try to listen into this, we use the readily available SDR software for that, or is there some kind of a extra thing you do to get it decoded off with FSK?
Did you catch that?
I caught about half of
Okay,
that. Did you
yeah,
catch
yeah.
that? I didn't catch
So the main telemetry and the actual data that we're collecting from the satellites is all encrypted. And so you could definitely receive it, you just won't be able to get anything out of it. However, the beacons are, as we were talking about, just those 2-line elements, and they're just transmitted in Morse code. And so that's something that you could absolutely listen in and pick up. And I don't know the exact resources or where you can go, but if you go online and look up, there's a whole community of people who are doing amateur radio to track down these satellites. And something that's really helpful to us, because when it gets, dropped out of the launch vehicle, we don't necessarily know where it is until someone picks up that signal and can tell us. And so, it's a big part of doing amateur radio for satellites like this. And if it's something that you're interested in, definitely something to look into.
All right, Abigail, Cole, thank you so very much. Thank you.